Now, you might be wondering what this has to do with chemistry.
Wait, this has to do with chemistry?
It all has to do with the mole.
Ew, aren't moles those gross hairy things like in Austin Powers?
No, not that kind of mole. In chemistry, a mole is a unit of measurement. 1 mole of any substance is equal to 6.02 times 10 to the 23rd particles of that substance.
Wow, that's 602 sextillion particles. That's a ton!
Not quite a ton. It all depends on what substance you're talking about, which is really the beauty of the mole.
Oh wait, I think I vaguely remember hearing something about this in chemistry class. Doesn't a mole of an element have something to do with the periodic table?
Yes, in fact, the mass in grams of 1 mole of any element is equal to the atomic mass listed on the periodic table for that element.
So, the mole is only good for elements, right?
Nope, you can also find the molar mass of pretty much any compound.
So, to find the molar mass of a compound, would you just add up the molar masses of each element within the compound?
That's right. So let's look at H2O, for example.
The molar mass of hydrogen is 1 gram, and the molar mass of oxygen is 16 grams. But since I have 2 hydrogens, I would multiply 1 by 2. Therefore, the molar mass of H2O would be 1 gram plus 1 gram plus 16 grams, or 18 grams.
Correct. You can also use the mole when dealing with gases.
Well, how would you do that?
Well, when looking at 1 mole of gas, assuming the gas is at STP, or standard temperature and pressure, 1 mole of gas, no matter what type of gas, will occupy a volume of 22.4 liters.
So let's put that into perspective. Okay, a soda bottle is 2 liters, so 1 mole of gas would fill approximately 11 soda bottles, with a little left over. Wow.
Hey, you guys still working on that project?
It's coming along.
Don't make a mountain out of a molehill.
Anyways, so how do all of these things relate?
Well, imagine counting out 602 sextillion particles. How many zeros is that?
I don't know, but that would be like this big.
Hang on, I have another idea.
Okay. Wow, that's a lot of zeros.
Yep, but instead scientists figured out another way. They just masked their sample.
That makes sense. So, by dividing the mass of their sample by the mass of 1 mole of the substance, they can find out how many moles they have and therefore how many particles they are dealing with.
That's correct.
But why the mole? What's significant about 6.02 times 10 to the 23rd?
Avogadro's number is significant because the atomic mass in AMUs of 1 atom of an element is also the mass in grams of 1 mole of that element.
Wow, that's pretty neat. So how can this be applied to real life?
Let's say you had 1 mole of Ford expeditions. And let's say all those expeditions had rear-ended each other in one giant line. How far would this stretch?
Probably pretty far. Let's see. So, 1 expedition is 205 inches long. 1 mole of expeditions would be 1.23 times 10 to the 26 inches, which is equal to 1.95 times 10 to the 21st miles. Now, it's 16 miles from my house to school and back round trip. That means a line of expeditions that have rear-ended each other would be able to make 1.22 times 10 to the 20th, or 122 quintillion round trips.
Holy moly!